Hey everybody, Mr. Gustin back in the physics classroom. Today we are looking at worksheet number 6. We're talking about circular orbits. So we've been talking about circular motion quite a bit, this unit and the centripetal force. Well, now we're talking about centripetal force and circular motion in terms of like planetary orbits. Okay, so we're going to be using Newton's law of gravitation here. Let's go ahead. I'm on worksheet number 6. I'm looking at problem number 2. If you haven't seen the video for problem number 1 yet, Mr. Bose does a great job of walking through. Scroll on up, use that shortened Google link, and you can see some work there. We'll do problem 2 together right here. So, first things first, I'm always going to draw a picture of my problem to make sure I have my ideas organized. The Earth goes around the sun in an orbit that is nearly circular. Let's go ahead and draw our sun. There it is. Oh, it's got some rays, bright shine. I'll get some sunglasses on it. Oh yeah. Awesome, look at that sun. Look at that. Our Earth is a little ways away. We're over here. You know what? We'll color our circle in so we can kind of see it on the whiteboard pretty well. And it makes a circular path. I'm not going to try to draw the whole circular path, but it's on a circular path. The first question, how much force does the sun exert on the Earth? How about the Earth on the sun? Well, we know that this is a third law pair, that the Earth and the sun both pull on each other with a weight force, or with a gravity force. We can describe that force mathematically by saying the force of gravity between them is equal to mama g, mass of the Earth, times the mass of the sun divided by the distance between the two of them squared. Now, it's not actually the distance between them squared. Let's talk about what this R value is. This R value is actually the distance between the center of both objects. So in this case, that's like the radius of the sun plus the radius of the Earth plus, I'll go over here, plus the distance between them. Like it's all three values. It's from the middle, from the nose of our sun all the way to the middle of our planet. That's what the radius is. So that's why I need to have all three added together into my radius. So, how much force does the sun exert on the Earth and the Earth and the sun? Well, we're going to go ahead and plug these values in. These values are all given to you right up above. So you're going to go find the mass of the Earth, the mass of the sun, mama g on the back side of your equation sheet, and the distance between the two objects, the radius of the sun and the radius of the Earth. You're going to plug it all in. Your answer will get spit out right there. I'm not going to do the math for you. You can do the math. That's the setup. That's the logic and the conceptual idea behind it. Now, question B wants us to calculate the Earth's velocity. Which direction does the velocity point? Is it moving at a constant velocity? Is it moving at a constant speed? Let's break these things down here first. We know that the Earth experiences, we know that the Earth is moving. Hopefully, we know the Earth is moving tangent to the circle that it orbits. The net force on the Earth is pointed directly at the sun. This is our centripetal force. The gravity by the Earth on the sun is our centripetal force. It's what keeps us in orbit. So, is it going at a constant velocity? Heck no. No. Constant speed? Yeah. Heck yeah. And don't Google me on that, right? It's not actually going at a constant speed, but on average, generally speaking, if we're going to generalize it as a circle, we can also generalize as moving at a constant speed. Now, it's not technically, but pretty darn close to going at a constant speed when we average this thing out. So, let's go ahead and calculate the Earth's velocity. What do we know about how long it takes the Earth to go around the sun? Well, we do know it takes 1 year to go all the way around the sun. It takes 24 hours to rotate on its own axis, but it takes a full calendar year to go all the way around the sun. It's actually less than 365 days. That's why we have this weird leap year thing going on. to make up for that. But we can do one of two things, right? The first thing we can do is go ahead and actually use the circumference of our orbital path and the period of the orbital path, right? That 1 year. That's one way to do it. But we also are like a little unaware of exactly the period of this motion, so we're not going to do that. Let's go ahead and be more exact. Let's use more exact figures. Let's go ahead and say, write an FC equation, or F net R equation, because this includes mv squared over r, and we know that the only force acting on the Earth centripetally is Mama G m Earth m Sun over r squared. Now we got to break this down. We got to remember, like, what is the r of this path? Are these the r's the same? Are these masses the same? So let's carry this down a little bit here. I want to make sure I write it nice and big for us so we can see these subscripts. Okay. Well, I see three m's. I see this mass, and I have no subscript. I see mass of Earth, and I see mass of Sun. My question is, which mass is this? Well, this is the mass that's associated with the centripetal force. The centripetal force tells us an object and its acceleration. What object is accelerating in this? Is it the Earth or the Sun? We're talking about the Earth. So this is actually the mass of the Earth. That's how I should label this. When I do that, I see this mass and this mass gone from our equation. Excellent. Are these radius values the same? Let's see. This is the radius of the circular path, and this is the radius of the circular path. So yes, these values are the same, which means I can drop out that r value and one of those r values. Let's rewrite this. Mama G, mass of Sun over the radius equals v squared. V must be equal to the square root of G, mass of the Sun, over r. Now, you can go ahead and plug those numbers in. You know the mass of the Sun. You know the distance between the nose of our Sun all the way to the middle of the Earth. And you know Mama G. You can take the square root of that to find speed of this object as it moves. Okay? You should be able to do that. I'm not going to do the math for you. C asks, what is the magnitude of the Earth's average acceleration in its orbit around the Sun? What direction is acceleration? Well, acceleration is another value we can find. If I go ahead, I'm going to erase this now, but I go ahead and I look at our equation sheet, it tells us the acceleration centripetally, this is problem C, is equal to v squared over r. It gives us this on our equation sheet. So let's just plug it in. I know speed from down here. I can plug speed in there. And I'm using that same radius value from before. I can just go ahead and plug that value in to find the average acceleration around the orbit. Which way is it pointed? That acceleration is radially inward. The acceleration's direction is changing constantly. We can always call it radially inward. Let's go ahead and look at question D. Question D is a little bit like what we did on worksheet number 5. It asks, what is the strength of the Sun's gravitational field when we are on the Earth? Or I'm sorry, on the Earth, rather, at the location of the Earth in our solar system. Well, the gravitational field, remember, the gravitational field is essentially the acceleration due to the Sun at the Earth's distance. On worksheet number 5, we talked about acceleration due to gravity, or the G of the Sun is equal to Mama G times the mass of the Sun divided by the radius squared. We loosely called this the gravitational field strength. I put, in my last video, I put like a dotted border to say this is what we call field strength. Okay, field strength is the acceleration due to gravity at some point in space. We will use this equation to use Mama G, mass of the Sun, and the distance from the middle of our Sun, the nose, to where we are in our orbit, the middle of the Earth. We will use that R value again. Again, the R value is the distance between the centers of both objects. That's the distance plus the radius of both objects. Okay? A lot of math involved here, some thinking. The concepts around circular motion are not new. The radially inward force is our centripetal force. In this case, it's only gravity. We're only dealing with one. Is the equation a little more challenging? Kind of. There's some nuance to it. There's some conceptual ideas to it. But you should be okay moving forward. Go ahead and finish worksheet 6. Good luck. I will see y'all back in class. See ya!